We've seen this connection now between radical expressions and rational exponents. And in this video, I'm going to use that connection to show us how to simplify radical expressions. I actually have a shortcut rule written on the board in front of me here, but in the first examples that I do, I'm going to convert these examples to rational exponents in order to simplify using exponential rules. Then we'll come back to the shortcut and use that later on. We're going to assume here that all of our variables represent positive numbers. If I don't make that assumption, there are times when I would have to insert absolute value signs into my final results. Because that's beyond the scope of this course, we're going to just assume that when we see an X or a Y, it represents a positive number, and we don't have to worry about absolute value symbols. Another thing I want to say is that this video is only going to cover roots of perfect powers. That is radical expressions that completely simplify. We'll look in the next video about what to do when part of the expression is a perfect power, but not the whole thing. So let's simplify the square root of y to the 14th. I'm going to rewrite this in its exponential form. So this has an index of 2 because it's a square root. That's usually assumed. And so I could rewrite this as y to the 14th to the power of 1/2. Then the way to simplify this exponential expression is to multiply 14 times 1/2. When I multiply 14 times 1/2, I get 14 over 2, or 7. So the square root of y to the 14th is y to the 7th. Let's look at this example. The cubed root of a to the 9th, b to the 6th. If I rewrite this in exponential form, it looks like this. A to the 9th, b to the 6th, to the power of 1/3. Remember, an nth root is a 1 over n power. When I simplify this exponential expression, I would multiply 1/3 by each of these exponents on the inside. So 9 times 1/3 is 9/3, which is 3. Let's go ahead and simplify that. 6 times 1/3 is 6 over 3, which is 2. So I end up with a cubed b squared. Now we see why my shortcut works. So I just said divide the exponent by the index, and that's exactly what happened here. If you want the square root of y to the 14th, you take 14 divided by 2, that's 7, and so your square root is y to the 7th. But it works because of the structure of the exponential expressions. Multiplying by 1/2 here is the same as dividing by 2. The same thing here. Taking a cubed root means a 1/3 power. Multiplying by 1/3 is the same as dividing by 3. And so I can use that shortcut of division to say the cubed root of a to the 9th, b to the 6th is a cubed b squared. That's just dividing both of these exponents on the inside by the index of 3. So moving forward, I'm not going to convert any more examples to exponential form. I'm just going to use this rule. Now, when we see a coefficient here, we have to deal with that separately. If there's a number in front of the square root or the cubed root, I have to take that separately. I can't divide a coefficient by the index. I can only divide exponents by the index to find the root. Let's look at a few more examples applying our shortcut rule of dividing the exponent by the index. Here I have the 5th root of 32, a to the 5th, b to the 10th. I'm going to separately compute the 5th root of 32. The 5th root of 32 is 2. So notice I'm not dividing 32 divided by 5. That would not be the correct answer. I'm calculating what number multiplied by itself 5 times gives me 32. Now I have a to the 5th, b to the 10th, and here I will divide the exponent by 5. So the result of this is a to the 1st, b squared. The 5th root of 32, a to the 5th, b to the 10th is 2ab squared. Here I have the cubed root of negative 27, a cubed, b to the 15th. The cubed root of negative 27 is negative 3. The cubed root of a negative number is negative. Remember, an even root of a negative number is not a real number. It's undefined in our context. And let's divide the exponents by 3. So I have a to the 1st, b to the 5th. Here's our cubed root. Now what about if there's addition or subtraction inside the radicand? Like in this example, I have the cubed root of a cubed plus b cubed. If I rewrite that in exponential form, I have a cubed plus b cubed to the power of 1/3. But we've already discussed the fact that exponents don't distribute across addition or subtraction. There's no way to simplify an expression like this. This cannot be simplified. So it might be tempting to say that this cubed root is just a plus b, but it's actually not the case. Just like exponents cannot distribute across addition or subtraction, a radical cannot be applied across addition or subtraction because it relates to an exponential expression. So I want to give a caution in general. The nth root of x to the n plus y to the n, I'm making this very general, is not equal to x plus y. I can't distribute across addition or subtraction. The same thing here applies if there's subtraction. The nth root of x to the n minus y to the n is not equal to x minus y. These radical expressions in general cannot be simplified any further.